Okay, let me start with page 22. For part E, we talked about from last session that this is basically a reworking of mean value theorem. The idea is that we don't have a G triple prime list of order pairs where we can figure out where it's going to cross, but we do have G double prime. So the idea is that, well, what if the slope between the endpoints of my G double prime graph is 2/5? If the slope between the endpoints of my G double prime graph is 2/5, I know that there must be a place where G triple prime is equal to 2/5. Okay, so it's basically taking that mean value theorem and adapting it. So mean value theorem looks like this initially. Slope between the endpoints is going to match with a specific slope at that point. And if we just take this mean value theorem and just let it go down a few levels, I can think of it the same way here. What if I'm looking at the G double prime graph? Well, the slope of the G double prime graph is going to have to match with the exact slope of that G double prime graph. Right. So I can take A and B. That's always provided for you. -4 and 6. So we do the change in G double prime over the change in X. So we look at 6 and -4. G double prime of 6 is 2. G double prime of -4 is -2. So change in Y over change in X, we get 2/5, then yes. Okay. If the average slope is a given value, we know that average slope must repeat itself somewhere along that curve. Okay, so by mean value theorem, since G double prime is continuous and differentiable, there exists a value where the derivative of that, the slope of that graph, is 2/5 on that interval. So let's part E. Let's look at F. Okay, let K be a function defined by K of X equals G prime of F prime of 2X minus 1. Find K prime of 3. To find K prime of 3, we first have to find K prime of X. To find K prime of X, we see that this is organized in this outside-inside portion, right? So we have to go through chain rule. So you got the outside portion, which is that G prime. You got the inside portion, which is that F prime of 2X minus 1. So we got to take turns with each part and put them next to each other. Okay, so let's build K prime of X. So G prime, this is a function notation. So all we can do is just make it go down one derivative, G double prime. Keep the inside portion intact. Times the inside portion's derivative, F prime of 2X becomes F double prime of 2X times what? Times what's inside this, right? So there's a 3 layers going on, right? Got the outermost layer, G prime. You got the inside F prime, and you got the innermost layer, which is that 2X. So each part needs its own space. Right? That's the hard part, trying to build that derivative. Any questions there? Okay, so from here, replace every x with 3. And then now it's just a matter of trying to get it down to a number. Two times 3 is 6. Okay, we can start with this f prime 6, because we need to know what this number is before we can decide what G double prime is, right? So f prime 6, we go to our table here. Whoops, we have to go to our graph, f prime 6. Okay, it's going to be 0. Sorry, this f double prime here. So f prime 6 is 0. Zero minus 1 is -1, so we end up with G double prime of -1 times f double prime of 6 times 2. So just trying to gather information one piece at a time. So G double prime of -1, we can get that from our table, which is -1. G double prime of -1 is -1. F double prime of 6, that's asking for the slope. This is f prime, so f double prime is a slope. So the slope of this line segment, I can just pick 2 points here and do slope, rise over 1, and go down 4 over 2. That's a slope of -2. And then times 2. Okay, questions there, part F. Okay, part G, find the maximum value of f on the closed interval from -4 to 12. So anytime I see the word maximum or minimum, I'm thinking extreme value here. So that means I got to test endpoints, I got to test critical points. Right, previously from parts B, I was able to, take this. Well, I'll go ahead and do this again. So this is the derivative graph. Anything on the x-axis is slope 0. Anything above is positive slope. Anything below is negative slope. So if you want to create a slope sine line, you know that your endpoint is from -4 to 12. You know your critical points are at -2, 2, 6, and 10. And then we just gather our information here from -4 to -2 below the x-axis, so negative slope, -2 to 2, positive slope above the x-axis, from 2 to 6, above the x-axis, from 6 to 10, below the x-axis, and then from 10 to 12, still below the x-axis. Okay, it's only asking for maximum, so we only need to pick out the relative max. So, and also some of these critical points are not even relative extrema. So 2 is not a relative extrema, and -2 is a relative minimum, 6 is a relative max, 10 is neither. So we only need to test out 6, -4, and 12. Any questions there as to why we're just narrowing it down to those three values? It's not wrong if we wanted to test the other values. It's just we know that it can't come from there, right? Maximum value can only be endpoints and relative max. Okay, so we have this derivative graph in front of us. We're going to be involving the area to get from f prime to f. There is no formula given to us, so we have to create our formula, which is our final position that we're looking for is the initial plus displacement. So we can start off with negative f of negative 4. Equals initial. Now, initial is always going to be whatever is given to you. Okay? It's not always going to start on the furthest left. It's always going to be whatever is given to you. So in this case, it's given to us as f of 10. So we have to start at f of 10 because that's an anchor point that's given to us. And we have to make our way backwards to negative 4. So displacement is whatever the region is from 10 to negative 4 of f prime. Now, notice that I'm going backwards here, but I'm forced into it because I'm starting here and I'm ending here. So I need to show that in my integral from 10 to negative 4. Now, we want to read the graph. So now that I have this down on paper, I can flip the bounds and change the sign so that I can read from left to right. But initially, when I place this on paper, I need to follow what the rule says, right? Initial to my end. Okay, so f of 10 is 5 minus so from negative 4 to 10, we have to go to our graph and look at all the regions that we've collected, right? So these are all triangles. They all have 4s. Now you could have just done 1/2 base times height and just put 8 here instead. I just decided that I was going to split them up into smaller intervals. So from negative 4 to 10, there's a 4 here. That should be 4. What did I put down? Yeah, it should be 4. I think yeah, that's right. Okay. So 4 ends up being the resulting value here, because I have negative 4 plus 8, which is 4, plus 8 is 12. 12 minus 8 is 4. Okay, so 5 minus 4 equals 1. Moving on to f of 6. Again, we have to start at f of 10 because that's what's given to us. Sorry, not 6 to 10, not negative 6 to 10. So 6 to 10, that's just going to be negative 8. And finally, f of 12. So f of 10 is again 5. Here, there's no need to flip the bounds because I'm going from 10 to 12. It's already in the order that I want. 10 to 12 is below the x-axis. These are the candidates that we're working with. The highest y value, that is what we're looking for, was 13. So that's our absolute max.
Okay, we already can bring the balance while we're writing out an equation.
That's fine, as long as you understand that you're flipping it and then you're changing your sign. Yeah, it's fine. Right, yep. Justification are the steps that you're showing. Yep. Choosing the correct interval values and showing the steps. Yeah, that's justification. You don't have to write any sentences. No, not even that. Yeah. Okay. Evaluate this definite integral here. Now, we know that anytime we have a extremely messy definite or indefinite integral, we know we have to go through U substitution, right? There's no rule that can handle such a messy thing here. So let's see if we can start by rewriting this problem and isolating and identifying our U value. So I see an opportunity for me to get a set of parentheses or a bracket to show up here. Okay, so if we want to choose a U value, we want to usually choose what's inside a set of parentheses. These parentheses are too small. We want something that's a little bit larger here. So it looks like that bracket, what's inside this bracket is going to be potentially a good fit for our derivative or for our U value. And if we look ahead, right, if we select the U value, we want a derivative that will match and cancel out. And we know the derivative of G prime is going to involve G double prime. So this is waiting for us to cancel out once we get the derivative. So that's a good sign that we're able to see a variation of the derivative waiting for us in this problem. Okay, so we start with our U value. Derivative. G prime, we got to go through chain rule. G prime of U becomes G double prime of U times U prime. Okay, we make our substitutions. These are the pieces that we're trying to substitute. We're always substituting what's inside the bracket and the dx. And we're hoping everything will clean up in a way where we can make this look a lot more manageable. G double prime of 2x matches, goes away. There's a leftover, what? 1/2. Yep, that 1/2 is going to have to stay in front. Now, if you are able to see, the whole purpose of U substitution is so that we can get it down to something that feels a lot more manageable, right? This is kind of hard to see, like, what is the rule here? This, right, we're able to get it all the way down to something that's very obviously just power rule. Okay, so we go through power rule. Add 1/3, add 1 to 1/3, so we get 4/3. Flip that 4/3 up, that's 3/4. 1/2 times 3/4. That gives me 3/8. Okay. I have two options here. Either I can bring this back in terms of x, or I can convert the bounds in terms of u. It feels more straightforward to bring everything in terms of x, so I'm going to bring that x back in. G prime of 2x. Okay, so now that I have my antiderivative in terms of x, I can work in my bounds from -1 to 3. Upper bound first. Okay, so insert the 3 in for x. 3 times 2 is 6. Let's resolve this. G prime of 6, you go to your table. G prime of 6 is 1. Prime of -2 is -1. Right. Cube root of 1 is 1. 1 to the 4th is 1. Cube root of -1 is -1. -1 to the 4th is 1. You can leave your answer unsimplified. That's perfectly fine. Or you can make it all the way down to 3/8 minus 3/8, which is 0. So once you get it, everything resolved, you don't have to clean up if you don't want to. That's any questions with H? Okay. Next page. Find the average value. So average value theorem. Sorry. Let me write out the original average value theorem and we can adapt it. Okay, this is the original average value theorem. But we want to find the average value of f prime. So oh, sorry. The original average value theorem is just 1 over b minus a, integral from a to b of f of x. So if I want to adapt it, f prime of c will be 1 over b minus a, integral from a to b of f prime of x. Okay, so really I'm just replacing every a and b with -2 and 8, and then just finding the area under my f prime graph. From -2 to 8, we know all this is, oops, areas of 8. So 16 minus 4 is 12. So 12 over 10 reduced to be 6/5. Okay, find the average rate of change. So average rate of change, that's another way of saying slope. So basically asking for the slope, the average slope of f prime. So f double prime is roughly f prime of b minus f prime of a over b minus a. Right? We're just trying to find the slope between the endpoints on my f prime graph. Okay, so f prime of 8, that's just asking for the y value. This is the f prime graph. So f prime of 8 is -4. F prime of 1 is 0. Sorry, f prime of 1 is right here. Sorry, is 2. Next up, let p of x be the definite integral here. Find the values of p of 1 and p prime of 1. So p of 1 should be pretty straightforward. We just replace the x with 1. P prime of 1, I'm going to have to go through second theorem. Okay, so I'm just replacing every x with 1. From -2 to 3. So that's an area of 1 right there. So I have 8 plus 1, which is 9. Okay, to find p prime of 1, I first have to find p prime of x. So this is second theorem here, because I have to find the derivative of an integral. Okay, so if you look, second theorem, it's on your formula sheet. All I do is I plug the upper bound into the function, then multiply by the upper bound's derivative. Replace x with 1. F prime of 3, you go to your graph. F prime of 3 is the order pair. F prime of 3 is 1. Sorry, 2. So over here is that 2, right? Right. Let me go back through A through E. Then I'll see if you guys have any individual questions for me. Back on page 21. Find f of 4, f prime of 7, f double prime of 7. We know this is the f prime graph, so if I want to find any value on the f of x graph, either there's a formula, there's no formula, so I got to go through final equals initial plus displacement. So f of 4 equals my given plus the region between 10 and 4. I need to adjust the bounds here from 4 to 10. And then just like how we did with extreme value theorem, we're looking for this order pair as well. So f of 4 equals 9. F prime of 7 is basically asking, this is the f prime graph. So f prime of 7 is just looking for the order pair. F prime of 7 is -2. The f double prime of 7 is the slope at this point of the graph. And we know this is a nice straight line. We can just find the slope of this line segment. So just do rise over run. Pick 2 points here, so I can go down 4 over 2. That's a slope of -2. Okay, part B, on what interval between -4 and 12 is the graph of f both increasing and concave up? But first, I wanted to create my slope and concavity sign line. So we just talked about this, how we can kind of label our derivative graph with those arrows. So anything above is positive slope, anything below is negative slope, anything on the x-axis is slope 0. So I start off with -4 and 12. My critical points, my x-intercepts, -2, 2, 6, and 10. And I'm just putting the arrows depending on where my graph lives. Below the x-axis is negative slope, above is positive slope, negative slope, negative slope. Now, my concavity sign line is based off of my peaks and valleys, my points of inflection. The points of inflection on my derivative graph is going to be found at the max and mins, right? So 0, 2, 4, 8, and 10. 0, 2, 4, 8, and 10. And now to interpret concavity off of the derivative graph, we look at the slope. So wherever the slope is becoming more is showing a positive, or becoming more positive, that's concave up, concave down, concave up, concave down. So I'm filling all of those alternating concavities. And now the problem is asking, where's the graph both increasing and concave up? So I try to match all the numbers so I can clearly see where's my graph going to be increasing and concave up. So in this interval here, from -2 to 0, you see concave up and increasing, and also from 2 to 4. Now, you can also pull this from the graph to confirm. Increasing would have to be above the x-axis, concave up would have to be positive slope. So basically looking for where is there a positive slope and above the x-axis. So you see it from -2 to 0, and then from 2 to 4. Right, those are the only places where I see positive slope above the x-axis, and that matches with what we see here. For part C, find the equation with tangent lines. So notice that there's a need for product rule first. Product rule, and there's a little bit of chain rule. So we got to go through the product rule. Okay. F prime g plus fg prime, 4x squared becomes 8x. We keep the g function intact, keep the f. When we get to g's derivative, g prime becomes g double prime, 2x times 2. Replace every x with -1. Get it all the way down to a slope value. But it's asking for the equation of the tangent line, so I also need to plug -1 into the original function to get the y value. So I have my order pair, I have my slope form. All right, part D. This looks like it could be a L'Hopital's rule problem because it's such a messy limit problem. But the first thing we do is we have to first decide what's happening, right? We can't assume that it's L'Hopital's before, unless we get a 0 over 0. So let's see what happens. So 2 in for all the x's. I get e to the g prime of 2 minus 1 over e to the 5th, all over g of 4 minus 4. G prime of 2, look at my table, that's -5. E to the -5 is the same thing as 1 over e to the 5th. So this ends up being subtracting out to be 0. G of 4 is 4. Look at my table. 4 minus 4 is 0. 0 over 0. Now this is the green light for L'Hopital's rule, right? We know the limit exists. There's a hole in the graph, but right now we're not able to see where that hole is pointing at, what the y value at that hole is. So we go through L'Hopital's rule because we can't factor and reduce using other methods. So we got to find the derivative of the numerator and the derivative of the denominator. So e to the u becomes e to the u times u prime. 1 over e to the 5th is a constant. That's going to go to 0. G of 2x becomes g prime of 2x times 2. That's a little bit of chain rule there. Minus 4 is a constant. That goes away to 0. So once we have a derivative version of the numerator and denominator, now this gives us another variation for us to evaluate the limit. Okay, so replace every x with 2. And I just get it all the way down to something that is a numeric value. Okay, so I just quickly ran through A through E. Beginning of class, I did page 22 and 23. So I think pages 7 through 20 also kind of circles around the same topics. So I figured maybe it's best to just see if you guys have any questions and just walk around and help you guys answer any individual ones that you have. Go into explain things on test. If it's like a mean guy, kind of.
Okay. Could you explain like what the explaining part is? Like, cause I did feel there's a little bit. I do.
Yeah.
So,
You're just basically rewording what you see there.
it's just the functions can show. I know you have to say functions can be efficient. On a,
And then since this
and then
produces
same number.
some number, then you know that this must, that this must agree.
Okay.
So really just rewording.
So for this one, so the only reason we would use second fundamental theory this is when we're taking the derivative of
An interval, exactly.
Okay, and then the other one that I had talked about, oh yeah, so for the first fundamental theorem of calculus, that's when you're going from, oh, sorry, right? That's when you're going from like the derivative graph down or to, like the regular graph.
That's right, from the derivative of
Okay.
the original function.
Okay, thank you. So yeah, I have a sports medicine field trip in like 20 minutes. So I was letting you know, can I make up the place tomorrow morning and tomorrow at lunch?
Yeah, I can do that.
What? Yeah, sorry, I've totally forgot about that. But it's break right now. I should have told you earlier.
No problem.
Yeah.
For the first problem, here are a bunch of steps to find the slope. Just I can look at it.
Oh, yeah, exactly. I just made it very specific, but yeah, you can look at the graph and do it.
Yeah.
I mean,
Like the under function, like it's.
no, yeah, none of that, but you know, like Angela equation. Yeah, so. No, it won't be a work problem per se. It'll be filled with this, right? It'll be very much like technical. Because this is the derivative graph, right? Right, but the integral of the derivative is the area of it.
So you can just
Is that like a?
You could, but this is what you have. If you really want to do it that way,
Yeah.
you gotta first update this to. But you don't know what happened for the dependence, you don't have a good sim question, how to guess it down. So the probability, if let's say everything is given at one function level, so you can, but this is not the same thing.
I know.
Right.
You can have this.
So, yeah, looks like the one.
That's not very good. That's not good. That's all.
Yeah.
Yeah, I think that's.